let's take a look at problem number 8. Go ahead and read it. You can see this is why I'm not invited to any pool parties anymore. Oh, there's Sadowski with his laser pointer going to show us some physics. Yeah, my friends don't like that very much. Alright, so anyway, so there I am, and I'm directing the laser at different angles, and let's follow the instructions, right? First thing we're going to do is draw the reflected and refracted rays. So maybe you just want to draw it for situation A first, just in case you're doing anything wrong. Pause the video when you do this, and then I'll talk about what it should look like. I really like to see how students draw this. So let's review here. Here we have a dashed line. What does the dashed line represent? The normal, right? Why is it drawn as a dashed line? Because it's imaginary. So can light reflect off of the normal? No. There's nothing there. It's not an actual surface. No, the solid line here between air and water is the boundary, so light's going to reflect off of that. So in this first situation, for example, the incident ray is going up and to the left. Which way should the reflected ray be pointing? Yeah, down and to the left, because it's reflecting off of this surface, like we saw with the mirror the other day. Now, if this is bothering you, you have trouble visualizing this, well, maybe turn your paper. If you turn your paper upside down, does that help? Does it make it easier for you to see? If so, that's fine. I mean, it'd be great if you don't have to do that, but if you do, I don't care, as long as you turn the paper back before you start writing things, okay? So let's go ahead and draw the reflected rays for these other two situations. It's always going to reflect down to the left, down to the left. Now, we know what angle it's going to be, because, we're trying to find the reflected and the refracted angle, and we know, of course, our law of reflection, whatever angle it makes with the normal here, is going to make the same angle there, and, don't take out a protractor and measure it, just eye it up. See if you can see an angle that looks like 25, an angle looks about 45, an angle looks about 60 degrees. I'm sure you can just visualize what that looks like. Okay, so then what about the refracted ray? Well, we think light's going from the water into the air, so is it speeding up or slowing down? Speeding up, of course, air is closer to a vacuum. So should it be bending towards or away from the normal? Away from the normal, right. So draw something in this medium here that's farther than normal, right? It's not continuing in a straight line. It's going to bend somewhat away from the normal. We don't know how much yet until we do the calculations, but you want to get in the habit of making these predictions ahead of time. So make the prediction for the picture for A, do the math for A, then draw the picture for B and do the math, and draw the picture for C and do the math, so on and so forth. And you don't show your work for all of them. You're really doing the same problem 3 times and really just trying to establish some patterns here. So if you want to show the work for the first one, that's fine, but in the end, you're just crunching the numbers and get the answers. And for each one, we're finding theta 1 prime, reflected angle, and theta 2, the refracted angle. And again, we know what theta 1 prime is. You don't show any work for law of reflection. So this is what your refracted ray should look like. Some angle, we're expecting some angle in the air larger than the angle in the water. Now, your answer is going to depend on whether you're using the 3 sig fig version of the index of refraction, 1.33, or the 4 sig fig version, 1.333. Different sources listed different ways. It's not going to make a big deal. You'll be off maybe a couple of tenths of a degree. But if you're doing the 4 sig fig version, you should be getting 34.3 degrees. If you do this 3 sig fig version, I think you get 34.2 degrees, a tenth of a degree. Fine. As long as you're close to that, everything's working. Does this agree with our picture? Yes. It starts at 25 degrees. It enters the air at 34.3 degrees. It's larger. Fantastic. So do the same thing for letter B. Draw the picture, do the math. Same thing for C. Draw the picture, do the math. So in picture B, again, it's not going in a straight line here. It's got to bend away from the normal. We don't know how much yet, but maybe something like this. If yours doesn't look exactly like mine, that's fine, as long as it bends to an angle larger than the incident 45 degrees. And when you do the math here, for the refracted angle, you should be getting 70.5 degrees or possibly 70.1 degrees. Fine. As long as you're in that range, things are going real well. For letter C, it's coming in at an even larger angle, so it's got to bend even farther away from the normal, so maybe something like this. It's supposed to go in a straight line. And then you do your math, and you get an uh-oh, right? Yeah. Error, domain error, syntax error, makes a frowny face at you, it stops returning your phone calls, it insults your mother. Okay, so what are you trying to get your calculator to do that it's just saying, nope, not doing that? Right, you're trying to take the inverse sign of a number larger than 1. We know that's not how trig functions work. The sign function can only return a value 1 or smaller, so mathematically this is an impossibility. But it also has some physical interpretation, a physical meaning to it. So see if you can figure out what's happening here physically that's causing a mathematical error. Well, if you're not sure, look at the patterns. We've increased the incident angle, and every time we increase the incident angle, what happens to the refracted angle? It increases as well. The more it comes in at, the more it has to bend away from the normal, and so it bends away from the normal some, bends more away from the normal, bends a lot away from the normal, and I guess at some point when you have a large enough incident angle, it's going to try to bend so far away from the normal, it just can't do it anymore, and it doesn't get out. And that's what actually happens here. The interpretation is that this light ray in situation C doesn't get out. It doesn't get into the air. So we have an uh-oh. So let's see if we can figure out what's going on here. This phenomenon is known as total internal reflection. I've always thought that if you're going to go to a battle of the bands with a physics-themed emo band, total internal reflection would be a really good name for it, right? Yeah. Okay, so let's draw a picture of what's going on here. We'll draw a generic boundary and normal. Maybe it's between water and air like our previous situation. We'll draw some sort of incident ray, and of course it's going to reflect on the other side at equal angles. And just like in the problem, we have our laser pointer, for example. We can direct the light at any angle we want at this boundary, but at some point it's going to refract so much we get to some interesting situation. So this angle here, theta 1, could be literally anything. But at some point, it's going to do something interesting. So we're going to rename this theta 1 as theta sub c for the critical angle, where something critically different happens. And at this particular incident angle, the refracted ray bends so much away from the normal, it's actually moving here along the surface. What angle is this that it makes here with the normal? What is theta 2 going to be? Yeah, it's a right angle. It's going to be 90 degrees. So let's use Snell's law and see if we can develop some sort of relationship here. Okay, so we know that theta 2 is 90 degrees, and we know sine of 90 is 1. Of course, that goes away to 1. And theta 1, when theta 2 is 90 degrees, theta 1 is the critical angle. So I'm going to replace theta 1 with theta sub c. This goes away to 1. And then just divide through, and here's our relationship. That sine of this critical angle, this angle, that incident angle that makes the refracted angle 90 degrees, is this ratio n2 over n1. This is the way we're going to box it in. It's maybe not the most useful way, but it happens to be the way that's shown on the AP Physics 2 reference table, so I figure it might as well be good enough for us too. Theta sub c here is called this critical angle. It is an incident angle such that, if you're at the critical angle, the refracted angle is 90 degrees. So what does that mean? Well, this critical angle is sort of like a dividing line between different situations. So theta 1 could be absolutely anything. So if, for example, theta 1 is less than theta critical, as it was in the first couple of situations we saw in problem 8, well then everything proceeds as normal and the light escapes. So as long as theta 1 is sufficiently small, the light's going to refract and escape into the new medium, everything happens like usual. It's when theta 1 is too large, when it's beyond theta critical, where interesting things happen. If this incident angle is larger than this dividing line theta critical, we get this total internal reflection and the light never gets out. It is trapped inside, which sounds like it's crazy, but it actually happens. And then in terms of the equation, what are N1 and N2? So N1 is the first medium. It's the medium that traps the light. The light starts in this medium, and in certain situations, it never gets out, so it might trap the light. N2 is the other medium. It's where the light, quote unquote, tries to go. I put tries to go in quotes because we're talking about light. It doesn't have wants and needs and desires, but you're directing the light at that medium, and maybe it doesn't get there. So you're trying to get it to go there, but in certain situations, it will never get there. What are those situations? Well, let's look at our picture here. In letter A, where theta 1 was pretty small, 25 degrees. Yep, got out, everything's fine. And then here we increased it, it was still getting out just fine, but at some point we've exceeded some sort of theta critical, at 60 degrees, for example, and it never gets out. So really, we should erase that refracted ray from the picture. Now the question might become, what happens at theta critical? Well, at theta critical, the refracted ray goes here along the surface. So do we call that refraction? Well, physicists themselves can't seem to agree on that. Some books will say, well, it does bend away from the normal, so there is a refraction happening. But other scientists will say, well, it doesn't actually get into the new medium, so that's really kind of part of refraction, so it doesn't really refract. So if they can't figure it out, then we're not going to really quibble about it. So you're never going to be asked what happens when theta 1 equals theta critical. It's just these two conditions here. Either theta 1's less than theta critical or theta 1's larger than theta critical. So let's calculate what theta critical is. Let's go. Oh, so here's just another picture just of a whole bunch of different sources of light, all starting in some medium, then trying to get it out into the air. And so here it hits dead on, and here it bends away from the normal some, and bends away from the normal more. At some point, it tries to bend so much away, it never gets out, and it's all reflected inside. Okay, so let's turn to problem 9 here. In letter A, we're going to do this. We're going to find the critical angle for this specific situation, light traveling from water into air. So I'm going to pause the video and calculate. Alright, so we're taking this equation here, solving for theta critical, and of course, what's the first thing we have to do to isolate theta c? Sure, we have to take inverse sine of both sides, of course. So this is what that equation looks like, and then it's just a matter of putting the right numbers in the right places. So in this particular situation, is N1 for water or air? Well, it's N1. It's where the light starts. We're going from water into air, so N1 is for water and 2 is for air. It's starting in the water and it's trying to get into the air, so here's where the numbers go. This is our index of refraction for water, this is one for air. Now, you never, by the way, have to memorize any of these indices of refraction. There'll always be tables given to you, but you really should know the index of refraction for air off the top of your head. It's easy, it's 1, and water is the second most common medium we use, so if you can remember 1.33 or 1.333, it's a good idea, but you never really have to memorize it. Okay, so you put the numbers in the calculator, and we have 4 sig figs here, so we're actually at 4 sig figs in our answer, and we get 48.61 degrees. And this definitely agrees with this original picture here, right? 25 degrees, less than 48.61, it gets out. 45 degrees, less than 48.61, it gets out. 60 degrees, there's the theta 1 is larger than that dividing line, that theta critical, the light is trapped inside. Let's try letter B here. We just switch it up a little bit. We change the media. So we're still using this equation. What's N1 and N2 in this case? Well, it's going from water into ice. From water, that's N1, into ice, that's N2. So it should look like this. It's starting in the water, going into the ice. Again, we've got 4 sig figs. We can have 4 sig figs in our answer, which is way more precision than we probably ever need. But we should be getting 79.11 degrees. So let's see if we can figure out, why it's interesting, what we can learn from this. So here is 48.61 degrees. That means that any angle, incident angle less than this, light can get out. If it's an angle beyond that, light cannot. And here we increase theta critical to 79 degrees. So now we've got a much wider range of incident angles that will still let the light escape. So why do you think that happens? Look at the numbers involved and see if you can draw some conclusions here. So hopefully what you see here is in part B, these indices of refraction are quite similar to each other. In fact, let's say it wasn't going from water to ice, it was just going from water to water, in which case there'd be no difference at all. Well then, if it's just going from water to water, nothing weird would happen. There's no way light could get trapped inside because it's never going to bend away from the normal. If it's going to ice, which is an index of refraction quite close to this, well, it's only going to bend a little bit different from what it is in water. And so we have a much wider range of incident angles because it doesn't have to bend that much more away from that incident angle. So with a minor difference in the media, we get a very large critical angle. There's going to be a wide range of angles that will still allow the light to enter the second medium. But in part A, there's a much larger disparity between these indices of refraction. Air is much different than water, so that restricts the angles of the incident angles that will allow the light to escape, making a smaller critical angle.